Okay, so in this section, we're going to talk about polynomials. Right? How do you add, subtract, multiply, divide them? How do you factor them? How do you evaluate them at particular values of x? All right, and so I'm assuming from high school you know what a variable is, what a constant is. Like terms basically means that two expressions have exactly the same variable part. And so, for instance, 43a to the fifth and minus 6a to the fifth have the same variable part, which is a to the fifth, and so they're called like terms. If there's anything different at all about the variable portion of an expression, they are not like terms. All right, so remember, with regard to arithmetic, we have all sorts of properties that enable us to compute. We have the order of operations, we have commutative property, associative, and distributive property. And so since an algebraic expression like a polynomial really represents an arithmetic one, in other words, when you plug a number in for the variable, you get an arithmetic expression, all those rules will apply for algebraic expressions. All right, and so let's actually start off example 1, just to kind of get the ball rolling with how you deal with algebraic expressions. Here's one, right? So you have a bunch of variables in here. Well, actually, that's 2, s and t. And what you want to do is you want to evaluate that expression for these particular values of s and t. So when you have to do that, what you do is you plug in that value for s everywhere it occurs in the expression. So you plug it in for that one, and that one. Notice here, I plugged it in 3 times. You're really plugging in a -1 for s, so I put a parenthesis around that -1, because remember, that square is going to apply to s. S here includes that negative, so you have to include it in parentheses so that you know to square that. And then likewise, I'm plugging in -2 everywhere I see a t. The minute you do that, you have this expression, which is basically what you encountered back in section 1.1, right? You wanted to simplify this, and so what do? You apply the order of operations. And so we'll start here inside the parentheses to get -5. Then we compute this guy, right? It's something raised to a power, right? -1 squared is +1, -5 squared is +25. And once we've done that, we have an expression here where there are both products and sums. Remember, you do all products going from left to right first, which means I'll multiply -1 and 25, and then these 3 guys to get 6, and then you add those to get -19. So why don't you try this your turn, right? You have this algebraic expression, and you have those values for the variables. See what you get. All right, so if you plug them in, right, remember you're plugging in 2 for x, -3 for y, -2 for z everywhere they occur, you get this algebraic expression. Perform the products as they occur from left to right, then add or subtract from left to right each time to whittle it down to 1. All right, we're going to skip example 2 for the moment, but I want you to, when you're looking through the supplementary videos, take a look at some of those so they tell you how to interpret words into algebraic expressions, right? It's kind of a precursor to what you call a word problem, right? So it wouldn't hurt to actually look at that now. We will definitely encounter those as time goes on in the course. All right, what I wanted to get to doing is start performing arithmetic operations on polynomials. So the first one is fairly straightforward. If you want to add 2 polynomials together, what you want to do is use our properties of being able to change order and being able to regroup things in a sum or a difference to be able to group like terms together. All right, and so what I'm going to do here, I actually put each term that was a different power in a different color, just so you kind of see which ones are like and which ones are not. So we have an x squared here and a -2x squared there. So those 2 are common, or like terms. Same way, the 2 and the 11 are both constant terms, no variable part whatsoever, so they're like terms. So having done that, I just reordered all the terms so that I grouped like terms together. All right, and you can envision here there being a parenthesis around the red terms and a parenthesis around the purple terms. All right, to add like terms, you basically just add or subtract the coefficients depending on the signs. That's how I'm getting a -1 here and then a 13 there. We consider that sum simplified when every variable power, so an x cubed, an x squared, an x, so on and so forth, only occurs one time, right? So you can't have multiple terms with the same power. That wouldn't be considered simplified. All right. So why don't you go ahead and try this your turn and see what you get. Same idea, only now when you're subtracting, remember, if you're subtracting an expression, that negative has to be distributed to both terms in that parenthesis that comes after it. All right, see what you get. All right, so as I just said, what we're going to first do is distribute that negative sign through, right? So I'm multiplying the first guy by -1 and the 5 by -1 to get those terms. Then what I want to do is, as above, I want to group like terms together. And so I want to group the x terms together and the constant terms together, which I've done. And then you simply add or subtract the coefficients of those terms to get the simplified result. All right. Oh, just a note here. Oftentimes, what people see the fraction, they get kind of crazy and they say, oh, I want to get rid of the fractions. Let me just multiply by 3. Problem is, you can't just multiply an expression by 3 without changing its value. Right? What you're really thinking of, I think, is when you have an equation and you multiply both sides by a number, that's perfectly fine. But when you just have an expression, you cannot just simply multiply it by a number unless that number happens to be 1 without changing its value. So just be careful there. All right, so how do you multiply two polynomials? Well, let's start simple. Right, we're going to start off with multiplying two single powers of x. Right? Well, what does x squared mean? X squared means x times x, and x cubed means x times x times x. So if I wanted to multiply x squared times x cubed, right, I had just got to put those expressions in for each of them, throw out the parentheses because we're multiplying everything. It serves no purpose to have them. But then realize you have 5x's being multiplied, right? By definition, that is x to the 5th. And so if you look from beginning to end, notice here, to simplify that product, all we really ended up doing was adding the exponents to get the 5. And so in general, we actually have this formula. No matter what the m and the n are, if I multiply powers with the same base, I'm going to add those powers to combine them. All right. So now using that idea, what if we're multiplying more elaborate things? All right, so we'll look at a few of these. We're going to look at the first one, and then we'll look at 2, and then we'll look at 3. All right, so for the first one here, you're multiplying these two terms. But remember, if you just have a coefficient in front of a variable part, you're just multiplying there. So in fact, we have 4 terms being multiplied here, right? So we know that multiplication is commutative and associative. So I'm going to multiply the 3 and the 7 together, multiply the powers of x together, and in so doing, I get a 21x to the 5th to do that. Right. For number 2, notice you have a monomial, so a single term, single variable part times a constant, times a sum or difference of a bunch of terms. We know that by distributive property, you just have to multiply every one of these terms by this guy out in front. And so to simplify, that's exactly the first step. I'm literally going to show you that I'm multiplying every term inside that parentheses by that 7x to the 6th. But the minute you do that, you're multiplying in each of these cases a monomial times a monomial, right? So you're really just back to this first example, right? We know to do that, you multiply the coefficients together, right, as I do here in these parentheses. And then you apply that property that tells us to add the exponents to simplify each of those products. In so doing, you get this final expression. All right, so the next level of complexity with these is, well, what if I have a binomial times a trinomial, right? So what if it's more than just a monomial times a polynomial? You have more than one term in both the things you're multiplying. Well, in that case, you do the same thing. You're just going to do it one step at a time, right? And so here, I have an x minus 4 times that trinomial. So I'm going to multiply everything in that trinomial times the x, everything in that trinomial times the minus 4 to get these two pieces. But now each of these pieces is just like it was in the previous example. You have a monomial times a sum, monomial times a sum. So what do? You distribute that x through all those terms, distribute this 4 through all those terms. Now you're down here, which is just like the first example. You multiply these two monomials together by multiplying the corresponding coefficients and then adding the powers of the x. Right? I do that to simplify each of these 6 terms. And then in the end here, you're going to add like terms, right, just like we did for the very first example when adding polynomials, to get this expression. Okay. All right. For part 4, people all, when you multiply a binomial times a binomial, people often are introduced to this notion of FOIL, right? It's an acronym that tell you first, outside, inside, and last. Perfectly fine. If you're used to that, don't worry about it. You can actually use that, no problem. But realize that's just a special case of what we just did, right? We just multiply 3x times both these guys, and then multiply the minus 2 times both those guys, and add them up. That's the result of FOILing, right? And then finally here, with computing this, the reason I write this out is that people sometimes forget themselves and they distribute that power to both terms of the sum, right? So mistakenly, people often square the x, square the 4, and get x squared plus 16. The problem is that's not what x plus 4 quantity squared is, right? What x plus 4 quantity squared is x plus 4 times x plus 4. And notice here, that's a binomial times a binomial. You're going to apply this FOIL method or the distributive property twice. You're not going to distribute a power, right? And so what you do here, you'd have the x times the x. It gives you the x squared. You do get a 16 because from the 4 times the 4, but you also have this outer terms and the inner guys you have to multiply together. Each of those gives you a 4x. That's where that middle term of an 8x comes from. Okay, so just be careful when dealing with binomials squared. You have that middle term that you have to account for. All right, I'm going to let you, on your own, attack these your turns, right? So you saw those examples. Try to emulate them and then check your results afterwards. Okay, and don't forget, even though we're not talking about these in the video, the solutions to the your turn problems are always at the end of every section, right? So even if you don't want to refer back to the actual video, you can look in the back of your section in your textbook. All right. The next thing we need to talk about is how you factor an expression, right? So you spend months, I suspect, in high school algebra doing this, almost ad nauseum, right? And there are 3 main techniques that you learn, right? The first one you talk about is a greatest common factor, right? So you want to figure out what is the largest chunk you could yank out of every term of an expression. And what you do is you pull it out and then you rewrite the expression as that thing times a simpler thing. In fact, that's what factoring means. Take something and write it as a product of simpler things, right? And so we're going to do that for the first one and the second one. We'll come back to these. Let me just talk about the methods first off. Then you talk about something called a difference of squares, right? So if you can rewrite a polynomial as something squared minus something else squared, turns out there's a nice formula that you can use to factor that into a product of nicer things. And then the final one is kind of there's a method to the madness, but it's really comes down to guess and check if you want to think of it that way. But with experience, those guesses come much quicker. It's factoring trinomials, right? So let's actually look at a couple of these just to get reacclimated to this notion of factoring. All right, so for the first one, for 15x minus 10, notice that you can you can rewrite the 15x as 5 times 3x and the 10 as 5 times 2. So each one of them has a 5 in common. So now you can yank out that 5 and rewrite this using the distributive property backwards as 5 times 3x minus 2. Right, so notice that, I mean, this expression is not horrid, but it is written now as a product of simpler things. Right, these coefficients are smaller, so arguably if you're trying to find where that guy is equal to 0 at some point, it's a little bit easier with the arithmetic to find where it's 0 than it would be for the original. Okay, not a dramatic example, but you get the point. All right, for number 2, same idea. You don't have to just yank out a single number or a power of x as a greatest common factor. It could be an entire expression that's common to both. Right, and so here notice that in this example, the quantity in parentheses, that 2x plus 3, is in fact a common factor of both pieces. So I could yank it out and then multiply it by what remains, namely the 5x minus 7. Okay, the next thing, I talked about a difference of squares, right? So what does that mean? Well, if you can rewrite a polynomial as, identify it as something squared minus something squared, it turns out that if you use that FOIL idea backwards, this difference is equal to this product. Right? And so let's just check that mentally. The first terms would be a squared. The outers are ab, but the inners are minus ba. ab and minus ba are opposites, right? They're the same. Remember, because multiplication, you can change the order. And so the outer and inner terms cancel out. And then the last terms are minus b squared, which is here. Right? So in fact, that is a true statement. Now, if you want to factor this guy, you have to rewrite each of those things as something squared. And that's what I do here. Notice 9x squared can be written as 3x quantity squared, right? And 25 is really just 5 squared. And so what you have, you can rewrite the original difference as 3x quantity squared minus 5 squared, and now use our formula with a equal to 3x and b equal to 5 to write it as this product. Okay? Notice this is in fact simpler because 9x squared minus 25 is a quadratic. It has a power of 2 on the variable in there, whereas these guys are both linear expressions, much simpler to deal with. All right, and then as to not confuse you with factoring trinomials, I know you've seen it before, so I'm going to not work through examples with you because I don't want to go against what intuition that you've already gained with it. Right? You've already have a method that you learned to use from whatever high school you went to, and so I'm going to defer to that. Right? I do have written solutions here of how I would have attacked it, but I want you to do this the way you feel comfortable. If you are completely rusty on factoring, I have posted a fairly long video on factoring techniques on the supplementary sheet. So definitely go to that link, and then you can review factoring all you would like. All right. Let's go. Okay, and then also try these your turns. I won't take the time in the video to do it, but again, they are all worked out in your manual. Okay, long division. We're not going to really need this very much, but I will go through it just to kind of remind you what's all involved. Let's start with this an arithmetic example. What if I wanted to long divide 527 by 4? Right? What you learn to do, I think in 4th grade, if I'm not mistaken, is you start from the left and you take the divisor and ask how many times does that guy go into the 5 evenly? And here you'd say once. Right, you put the 1 up there, you multiply the 1 times the 4, and then you subtract that from the 5. That gives you 1, and then you bring down the next guy, right? And do the whole thing again. How many times does 4 go in evenly into 12? Well, the answer is 3. Multiply the 3 times the 4 to get 12, subtract those guys, so now you get 0, bring down the 7, do it again. All right, so how many times does 4 go into 7 evenly? Once. Multiply the 1 times the 4 to get 4, subtract to get 3. There's nothing else to bring down, and so this turns out to be your remainder, which you write as R3. Right? But technically, don't forget, when you're dealing with real numbers, we get away from that pretty quickly once we understand what fractions are. We would really write this as 131 3/4. Okay. All right, so when you long divide one polynomial by another, same exact trick works. You just have to be careful with the signs. All right, so let's look at how we would long divide this quadratic expression by x plus 3. Okay, so we'll just kind of work through it right from this point. So the first term is the 2x squared. How many times does x go into 2x squared? So what does that mean? It means, what do you multiply x by to get 2x squared? Well, you multiply it by 2x. And so if I multiply 2x by x, I get 2x squared, but you also, part of the divisor is the 3, so I'm going to multiply 2x times 3 to get 6x. I'm going to subtract that, like I did up here. Notice I multiplied the 1 and the 4, and then I subtracted it from that term, right? Right, well, if I'm subtracting it, I'm going to have to subtract it from those, these two terms here. Oh, I cannot do that. And so if I do that, I have to subtract a binomial. Don't forget, you have to distribute that negative sign through. And so I'm going to subtract 2x squared minus 2x squared. They have to go out. And then 7x minus 6x is the x. Don't forget to distribute this negative sign through those terms. Okay. Once you're to this point, you bring down the other term and you repeat the process. In fact, you repeat the process until the power on this guy is strictly less than the power of the divisor. Right? Here the powers are the same, so you go through it and do it again. Well, what do you multiply x by to get x? You multiply it by 1. And so if I multiply this whole thing times 1, what I'm end up doing is subtracting x plus 3 from that previous step. But to subtract it, remember, you're distributing those negative signs through both terms. The x's cancel, which they will always do. That leading term will always cancel by how you chose the part up here in the quotient to begin with. And then 4 minus 3 is 1. Right, so your remainder is 1. And so in the end, the quotient technically is 2x plus 1, remainder 1, but I don't want to write it like that. I want to write this as what we're going to call a rational expression in the next section. Namely, write it as 2x plus 1, and then plus that fraction. It's 1 over the divisor. All right. Here, same sort of idea. We have a cubic divided by a quadratic. Right, and so the only caveat here, we just have to be a little careful, is you want to put in placeholders when certain terms don't exist, right? So here we had an x cubed term, and so technically if it's a polynomial, if that's the highest power, you can have an x squared and x and a constant term. We happen to have all 3 here, so there's no need for a placeholder. But technically the 6x squared doesn't have to be there, right? If it wasn't there, I would have wanted to insert a 0x squared here just for bookkeeping's sake, right? And that's what I'm doing here with the divisor, right? Notice that x squared minus 1 is a quadratic expression, has power 2. And so technically there could be an x term in there if there had wanted to be. There isn't one. But I want to keep track of that term, so I line things up appropriately. So I'm just going to put a 0x in there to keep track. All right. Ask the same questions again as you did before to compute this long division. I'm going to multiply, what do I multiply x squared by to get that leading term of x cubed? You multiply it by x. And so I'm going to multiply every one of these terms by x. That gives me an x cubed, a 0x squared, that should be an x squared here, to make that comment. Right, not on this guy, just make that an x squared. And then minus x is that guy. But I'm subtracting that, so I'm going to go through, I'm going to subtract, so I'm going to change all the inside signs and then add down. The x cubes go. I have a 6x squared minus 0x, which isn't going to do anything, and then a minus 2x plus x, which is minus x. Notice the x squared and the x squared here are the same, so I do it yet again. What do I multiply x squared by to get 6x squared? 6. All right, so I take the 6, I multiply by every term in the divisor. That's how I'm getting these terms inside the parentheses. And then I'm going to subtract that off to get minus x plus 1. And so this quotient is equal to x plus 6, that's the quotient, plus this remainder. Okay, and I'll leave you look at the your turn on your own. Okay, and that brings us to the homework section. So it's really a lot to review at one time, right? Especially if you haven't seen this stuff for a couple of years, you know, going through adding, subtracting, multiplying, factoring, and long dividing all in one time can be a little bit intimidating. So what I suggest you do, make sure you go through all the your turns that we did not complete together, and then view those supplementary videos that I uploaded to the supplementary sheet, and then attack the homework problems and see how it goes. All right, try that and let me know how it goes.